Okay, so first part of today's class is ANOVA, plan comparison of means. We'll go over what we do once we've rejected the null hypothesis for a analysis of variance, one-way analysis of variance. So as we ended last class, we rejected the null hypothesis for our study of perceptions of government among college, university undergrad, and university grad students. And written up in APA format, we reached the conclusion that perceptions of government scale, score, means, and standard deviations for the three groups are provided in Table 1. The one-way analysis of variance revealed a significant effect for the factor group F with 2 degrees of freedom between groups and 24 degrees of freedom within groups. The F observed is 10.76, P less than 0.05. So I had my alpha set to 0.05. Okay. Once we got into this point, the analysis of variance is just that, an analysis of variance. And rejecting the null hypothesis means that the variance between groups is much larger than the variance within groups. So for the total variance for the whole study, partitioned into the two pieces, the variance between groups is a significant contributor to the total variance. And it outweighs the within groups variance by a factor of 10.76, which we see from our F ratio. And as we said last week, the F ratio tells us that the between groups variance is 10.76 times larger than the within groups variance. Okay, so key thing here is I know that there are differences amongst the means, but I don't know specifically where the differences reside. So as you recall, the null hypothesis is mu college equal to mu undergrad equal to mu grad, right? The alternate hypothesis is HO is not true. And saying that HO is not true leaves it fairly wide open as to where amongst the means in the population the differences reside, right? It could be that the two university groups are the same, and those two university groups differ from the college group, or the college and undergrads are the same and they differ from the grad students. It could be that all three groups differ from each other, or it could be the college and grad students are the same and they differ from the undergrads. So there's a fairly wide range of possible outcomes here in terms of where within the population the differences amongst the means reside that led to my rejecting the null hypothesis for my analysis of variance. Okay. So there are differences amongst the means. Now we need to look at ways of finding where those differences reside. And we're going to look at two classes of comparisons. One way we can do this, and we're going to do this in this part of the class, is we're going to look at complex comparisons, right? We can combine groups together and compare two groups to another group. And in this case, the two comparisons that the one thing we can do is we can compare the college students to the university students, knowing that the university students are made up of two subgroups, the university undergrads and the university grads. So conceptually, it makes sense to say, okay, let's just compare the college students to the overall university students, knowing that the university students are made up of two subgroups. We can also do what's referred to as simple pairwise comparisons, right? I could compare the college to the undergrad, college to the grad, and then the undergrad to the grad, right? Those are simple pairwise comparisons of the means that I have within my study. We're going to look in this part of the class at doing both complex comparison and also a simple comparison. Okay. There are two general classes of comparisons. There are what referred to as planned comparisons, and there are post hoc comparisons. So the planned comparisons can be considered analogous to having our one or two-tailed alternate hypothesis. With a one-tailed alternate hypothesis, I have specificity, right? In terms of a single means t-test. I'm kind of like in fairly, with the existing body of literature would suggest that my sample mean, the population mean for my group is less than the expected population mean, right? Mu less than a given value. That's specificity. And when I have specificity, I have a more powerful test because with a one-tailed alternate hypothesis, my 0.05 alpha, that 0.05 is concentrated in the one side of my a distribution of sample means, or my t-distribution, right? So it's in that one side, mu less than a given value, I expect a negative t. For a two-tailed alternate hypothesis, I have to take that 0.05 alpha and split it in two, right? 0.025 goes down into the bottom tail, the negative side, for mu less than a given value. And then I have to give the other half, the other 0.025, in the plus side of the tail for mu greater than a given value, right? And plan comparisons are very similar. When I have plan comparisons, I have structure. I have an existing body of knowledge or research that can direct me into looking at very specific comparisons amongst the means. And there is a number of restrictions to those comparisons, and I'll explain those in a sec. Post hoc comparisons are really for research that's more exploratory, right? It's research where there really isn't a solid body of knowledge upon which to develop very specific comparisons. When I do post hoc comparisons, I typically do all pairwise comparisons. And we know the trouble that gets us into when we do all pairwise comparisons. Post hoc comparisons, what they do is they make it harder for you to reject the null hypothesis, because they look at, as we talked about last week, they look at the family-wise error rate. So if I have three means, all pairwise comparisons, I can compare three groups. I can have three comparisons, right? College to undergrad, college to grad, undergrad to grad. When I do that, I'm doing all possible pairwise comparisons. And that's typically what post hoc comparisons are. I just look at all possible pairwise comparisons. In my study, I have three. When I do this, as we'll see a bit, my family-wise error rate for type 1 error, or alpha, is not 0.05. It's actually 0.14 at the family level. So what post hoc tests do, they take that into consideration and they make it harder for you to reject the null hypothesis. Most do. Some don't. We'll look at that in more detail in the second part of this class. Okay, so for a plan comparison, what you're doing is you're doing things in a very planful way. You specify your comparisons that you want to complete prior to collecting your data, right? So this is all done during the proposal development phase and the study, your research design phase. You don't have to use the F observed, but what you do need is you need an error term. And the error term that you use, and what we will use in this case, is the MS within groups. And it's just part of the tradition. So you don't need the F observed. Okay, we'll get into that a bit more. You set alpha for each comparison to 0.05. So you don't have to make any adjustments. Each comparison should be independent of all other comparisons. And I'll talk about what I mean by that a little later. Okay. When we do complex comparisons of means, and we group, say, for example, the university students into one mega group, we have to look at combining two groups to create a super mean in terms of, take the combine the college, collapse the college, the university undergrad and the university grad together. We had 9 students per group. We collapsed them together to 18 to calculate the mean that is just university student, and not factoring and not splitting them apart into undergrad and grad. Okay. For everything we do for plan comparisons throughout the remainder of this course, we're always going to have equal ends. And with equal ends, it's fairly easy to create combined means. Because each mean is made up of the same number of subjects, all I have to do is take the mean per group that I want to combine, add the 3 means together, and multiply them by 3, or divide them by 3, right? Because they're the same number of subjects per group. So we're always going to have equal ends. It makes it easier. It makes it a little harder when the ends are unequal, but we're not going to worry about that. But we will use this because, for example, if I want to combine the undergrad and grad students into the one group called university, I take the mean for each group, add the 2 means together, and then divide by 2, right? And that's going to form the basis of my complex comparison. So I just want to be clear, moving forward, to make life easier, whenever we do anything in analysis of variance, we will always have the same number of participants per group. When we don't have an equal number of participants per group, we'll let SPSS take care of that. I don't want to get into the messiness of those calculations. I want to keep everything nice and clean and simple so it's easier to understand what the hell it is we're actually doing. Okay. Now, when I do calculate a mean that's basically three groups collapsed together, I take each mean, add the means, and add them together. So I take the 30.4 plus the 62.1 plus the 116.3, add them together and divide by 3, right? This is doing it for style and look. What I can do, instead of adding the three means together and dividing by 3, I can take each mean, multiply it by a third, do that for each of them, and then add them together. So what it means is M1 plus M2 plus M3 divided by 3 is the same as 1/3 of M1 plus 1/3 of M2 plus 1/3 of M3. The only reason I'm doing this is for style. And it also structurally makes sense in terms of what SPSS does. And you're going to be using this in SPSS. Okay, so it's 1/3 M1 plus 1/3 M2 plus 1/3 M3. Okay. Okay, so my first plan comparison that I want to do, and I'm going to do 2 plan comparisons. Now the number of plan comparisons I can complete, I'm restricted to the number of between groups degrees of freedom. So much like if I go back to my original source table, I don't have the original source table here. My between groups, my total degrees of freedom for the whole study was 26 from my source table. The within groups error degrees of freedom was 24. The between groups degrees of freedom was 2, right? It's K, which is the number of groups minus 1. Structurally, what I'm doing is, and we know that, the sum of squares total is equal to the sum of squares within groups plus the sum of squares between groups, right? It's total sum of squares is partitioned into those 2 pieces. I also know that the degrees of freedom total of 26 is separated into the within groups degrees of freedom 24 plus the 2 degrees of freedom between groups. So the 2 plus 24 equals to 26. What you do with plan comparisons is, and this is the structure of it, you're further partitioning those 2 between groups degrees of freedom. And each plan comparison takes up 1 degree of between groups, one of the between groups degrees of freedom. So I'm partitioning the between groups degrees of freedom, the 2, into 1 degree of freedom for one comparison and 1 degree of freedom into a second comparison. So really what you're doing with plan comparisons is further partitioning the degrees of freedom for the between groups degrees of freedom, right? So, okay. So P1, my first plan comparison, I want to say, okay, you know what? I've got a significant effect here. I've got college and I've got university students. So what I want to do is I want to compare my college to the university. So I want to collapse the 2 university groups into 1 mega group, which is just university students. So the null hypothesis for P1 is the population mean for the college students is equal to the population mean for the university students. The university students are made up of grad students and undergrad students. So, and I know there's a population mean for the grad and a population for the undergrad. So what I'm saying is I can take the university grad population plus the university undergrad population mean, add those 2 together, divide by 2. That'll give me the population mean for university students in general. So mu college is equal to the population mean for the grad students plus the population mean for the undergrad students divided by 2. They may differ slightly, but I'm saying overall that university students as defined as a population that's made up of grad and undergrad differ. Now, the university grad and undergrad may themselves differ. Those 2 population means may differ, but when I combine them together as a collective university students, they don't differ from the college students. Because then what I can do after is, okay, University grad plus and university undergrad, they may themselves, the population means may differ, but when I think of them collectively as university students, they don't differ from college students. My next plan comparison will say, okay, well, maybe there's no difference between college and university students, but the source of my significant analysis of variance table may be that the real difference is nested within the university students. And it's the grad students who have a more popular perception, a better perception of government than the undergrad. That's where the difference in my study resides. And that's what we're going to see. We're going to see that there's no difference between college students and university students in general, university in general. But the real difference is once I delve into the university students, is that the grad students have at least in my study, have a much more positive perception of government than the undergrad students. So, and the key thing here is the logic makes sense, right? If I got two plan comparisons I can complete, it makes sense to say, well, let's compare the college to the university students and see if there's a difference. And also, let's then go within our university students and see if there's a difference between grad students and undergrad students. Okay. The next phase is, as I did before, I'm going to put my null hypothesis in fraction form. Well, first of all, I'm going to move them over so that they're equal to 0. So population mean for college minus the overall mean for university students, which is mu grad plus mu undergrad divided by 2. That equals 0. Then I will put it in fraction form, right? So mu grad plus mu undergrad divided by 2 is the equivalent of 1/2 of mu undergrad plus minus 1/2 of mu grad. Fair enough. Then the next step is to put it in clean standard form, which we will use in SPSS. So put a 1, even though you don't really need to see it, but you're going to need it in SPSS. So +1 for the university college, and then plus minus 1/2 undergrad plus minus 1/2 grad equals 0. So in general form, my plan comparison is, in terms of the structure of it, P1 equals the sample mean for the college students times by +1, which is kind of like a meaningless step, but it is important. We'll see later. Plus minus 1/2 times by the sample mean for the undergrads plus minus 1/2 times by the sample mean for the grads. So here is my null hypothesis. That translates into the actual plan comparison that I complete, right? So P1 is +1 times by the sample mean for the college students minus 1/2 times by the sample mean for the undergrads plus minus 1/2 times the sample mean for the grad students. That is the structure of a plan comparison. And we put it in this form. The numbers in brackets are referred to the coefficients, right? So the coefficient, the C for the college students is +1, the C for the undergrad students is minus 1/2, and the C for the grad students is minus 1/2. So in general form, the plan comparison P1 is equal to the sum of the CMs. The sum of +1 times by M college plus minus 1/2 times by the mean of the undergrad plus minus 1/2 mean of the grads, right? So in general form, a plan comparison is the sum of little c, capital M. Okay. Now, here is it in standard form. A plan comparison P is equal to, per group, CK times by MK, and I sum them up, right? And we will always talk about it in general form. So I have the coefficient C for the college students times by the sample mean for the college students plus the coefficient for the undergrad times by the mean for the undergrad plus the coefficient for the grad students times by the mean for the grad students. And then, as I saw on the last slide, that's what it kind of like folds into. In general form of plan comparison, the sum of the coefficients has to add up to 0, right? It's like, the way the sum of the values for the mean, like the sum of the deviations from the mean, always the negatives add up to the positives, right? It always sums to 0. We must have that in our coefficient here. So the number of the sum of the plus coefficients has to be equivalent to, on the negative side, the sum of the negative coefficients. So +1 minus 1/2 minus 1/2. Minus 1/2 plus minus a half, and a minus a half equals minus 1, right? So plus 1 compared to minus 1. So the sum of your coefficients, as a test, the sum of your coefficients must always add up to 0. Okay. So that's our, basically, that's our denominator for what is essentially a t-test. Okay. A bit of a redundant slide, but let's keep rocking. Okay, so yeah, so plus 1 times the mean of K1, which is college, minus a half times by the mean of the undergrads, minus a half times K3, the mean of the grad students. Now, my 0.5 is equivalent of 1/2. Now, I do that, and I can see that plus 1 times by 25 is 25. Minus a half of 30 is minus 15. Minus a half of 20 is minus 10. Minus 15 plus minus 10 is minus 25. So in this case, there is clearly no difference between the college and university students when I collapse them together. And once again, my coefficients add up to 0, right? 1 minus a half minus a half. The actual plan comparison, the sum of the CMs, also adds up to 0, which tells me there's absolutely no difference between college and university students when I define university students as the undergrad and grad students, right? So the college student mean was 25. Half of 30 is 15. Half of 20 is 10. There's a minus, so that's minus 15 for the grad students, minus 10 for the undergrad students when I combine them together, right? You know, minus a half times 30, minus a half times 20. So that comparison, I'm done with it. I don't have to do anything more. It actually is 0. I could just say, okay, well, there was no difference. So the t observed for the comparison of the college and university students was 0. So my significant F test, you know, that 450 I had in my source table for between groups, it's not due to a difference between college and university students. So I know, I'm pretty confident that the true difference in my study is the grad students have a much higher perception of government than undergrad students. That's where the difference resides. So the difference doesn't reside in the comparison between college and university. The source of my significant analysis of variance F test is nested within the university students. The grad students have a much higher perception of government, much more positive perception of government than the undergrads. And that's what we'll do next. Okay, so now we're going to put this, we're putting it in standard form, right? Because a plan comparison is the sum of the CMs. I'm always structurally going to have it the same. Parts of it are going to look redundant. So my second plan comparison, which is a simple comparison, a simple comparison of two means, pairwise comparison. Compare mu grad to mu undergrad, right? Null hypothesis, there's no difference between the two. Alternate hypothesis, two-tailed, there is a difference. Mu grad minus mu undergrad equals 0. In standard form with coefficients, right? I want to put it in standard form. I put in a 0 for the college students, and we'll see in SPSS why this is important. I have to put that 0 in, so that at least it has a comparison, because my general form is, my comparison is the sum of CMs. And in the sum of CMs, I have to make sure when I'm summing across that every mean is included, even though it gets zeroed out. So the coefficient for the college students is 0. I zero them out and wash them out. So they're out of my plan comparison. For the undergrad students, it's 1. For the grad students, it's minus 1. I then make it a summation, right? So I put the minus inside the bracket and make it so that it's, you know, coefficient mu college plus coefficient undergrad plus coefficient grad, right? So this is just structurally to put it in a standard form where the comparison is the sum of CMs. The sum of CMs, coefficients and means, collectively across the three means is 0 times by the mean of the college plus 1 times by the mean of the undergrads plus minus 1 times by the mean of the grads. What do my coefficients add up to? And they must always add up to. They add up to 0. Okay, we're rocking here. We'll walk through this. I'll do this. We'll do it in Excel in a bit. So the sum of my CMs, this is a plan comparison in general form. A plan comparison is simply the sum of CMs across each of my K groups. K equal 1, 2, and 3. So 0 times by 25 is 0, plus 1 times by 30 is 30, plus minus 1 times by 20 is 10, minus 10. So the p-value is going to be minus 10. The sum of my C's must always add up to 0, right? So 0 plus 1 minus 1 equals 0. Okay. Now, I did say that my comparisons have to be independent of each other. And we use the term independent, and a synonymous term for that is orthogonal. And we use the term orthogonal, and orthogonal means that the comparisons are at 90 degrees. 90 degrees. Why do I even use that term? Well, because behind the scenes, these types of analyses are done in vector space, right? So they're done in using matrix algebra, and matrix algebra representing n-dimensional spaces. And n-dimensional spaces means that the dimensions upon which, in this case, my comparisons are at 90 degrees, which means they're independent of each other. They're not kind of like wonky at weird angles. So in that case, to ensure that my comparisons are orthogonal, the little test that I do is I multiply the coefficients per group for my two comparisons together. So I take, here's my first comparison, which was college compared to the two universities. The coefficient was 1 minus a half minus a half. My second comparison was undergrad to grad, which was 0 for college, plus 1 for undergrad, minus 1 for grad. I take the comparison for the two coefficients for P1 and P2 for the college students are 1 and 0. So plus 1 times by 0. The coefficients for the undergrad was minus a half times by plus 1, minus a half times by plus 1. And then for the grad students, it was minus a half times by minus 1, right? So minus a half times by minus 1. If I take each group, each K, and multiply the two coefficients across the two comparisons for that group, and do that for each of my three groups and add it up, my comparisons are orthogonal or independent of each other when the sum of the multiplication of the coefficients per group, when I add that up, it's got to add up to 0. If it doesn't add up to 0, my comparisons are non-orthogonal, or they are not independent, which is terrible. In our case, I will always make sure that when I ask you to do plan comparisons, they will by definition be orthogonal. So when you set up the coefficients for each of the plan comparisons, for any of the practice questions we do, or any of the test questions or assignment questions you do, the comparisons I ask you to do will be orthogonal. It's cleaner, it's just good research design. Okay, the final piece is I'm really calculating a t observed, right? And a t observed is a difference between two means, an independent means. It's actually a single means t-test in this case, and a standard error, right? The denominator, which is, in our case, the funky formula for the standard error for the t-test for a plan comparison is the mean square error, or within groups, from your original source table, multiplied by the sum of the coefficient squared divided by n, right? So this is your kind of like an independent means t-test funked up standard error. It kind of roughly looks the same, but it's not, right? It's the square root of something. Okay. And that's my t observed with 24 degrees of freedom. So since our denominator is tied to our standard error, and our standard error has 24 degrees of freedom, each t-test for a plan comparison, the degrees of freedom are the within groups degrees of freedom, right? Okay. So in our P2, which is comparing the undergrads to the grads, my t observed, my standard error is the 20.9 from the MS error multiplied by the sum of coefficient for group 1 divided by the n for group 1, coefficient for group 2 divided by n for the n for that group, and the coefficient for group 3 squared multiplied by the n, right? So it's a relatively clean formula, but the guts of it are typical independent means t-test standard error. I'm not doing pooled or anything like that, and I'm not adjusting the error. My standard error is 2.155. My t observed is the p-value, which is really a comparison of means. In this case, it's a simple comparison of undergrad to grad, right? So it really is independent means t-test. So minus 10 divided by my standard error equals minus 4.64. My degrees of freedom are my within groups degrees of freedom, which is the total degrees of freedom minus k, which is 24. T critical for a DF equal to 24 and a two-tailed test is plus or minus 2.064, right? And that's from our source from our T critical. Okay. My T observed is negative 4.6. It is in the critical zone. It is more extreme than negative 2.064. I reject the null hypothesis. I therefore conclude, based on my planned comparison, that the university students had a much more positive perception of government than the undergrad students. Okay. Okay. Now, by definition, with your planned comparisons, all you need from your source table is your mean square error. You technically can, if your planned comparisons are orthogonal, and you only have 2 of them, then you can actually skip your F test. You don't even have to look at whether your F observed is significant or not and jump immediately to the planned comparisons. Doesn't happen often, but it does happen. Okay. Typically, you have to report the omnibus F test anyway. That's typically what most publications expect, but that's getting nitty-gritty technical. Oh, I don't have my write-up. Let me see here. Let me just pull up there. I'll fix the slide. There we go. So the means and standard deviations for the 3 groups are provided in Table 1. The one-way analysis of variance revealed a significant effect for the factor group, right? So there's differences somewhere amongst the students. I don't know where it is. Following planned comparisons were completed. College students compared to the undergrad and the grad students. So college compared to university, and the undergrad compared to the graduate students. The first planned contrast was not significant, t equal to 0, because there was no difference between those in that complex comparison. But the second planned comparison was significant, t24 minus 6.44, p less than 0.05. The results showed that the grad students had a more positive perception of government than the undergrad students. Voila. Now, for the next part, I'm going to just walk through the calculations in Excel and SPSS.